Hello, this is Professor Muhammad and this is Engineering Mathematics class, and this is video number 6. We are going to talk about the linear second order differential equation, and today I'm going to talk about one part, or part number 1 of this topic, linear second order differential equation. Okay, so this is, as we said, we are going to make a definition actually for the linear part here, the meaning of the linear second order differential equation, and I think that we should jump directly to this slide. Let me use the pointer here. So first, the second order differential equation in general, okay, second order differential equation is, the meaning of it is the one which is containing a second derivative, but no higher derivative. This is the meaning of the word second here. Second derivative, which is y double prime, for example, but it is not a higher derivative. Okay, second derivative, which is like u double prime, for example, but no higher derivative. We're not going to find higher derivative like triple derivative, something like this. The theory of the second order differential equation is, actually it's very big and very vast, okay? And we are going to focus on linear, okay? Call it linear second order differential equation, which have many important uses. And you are going to find that you are using this technique for the solution for the linear second order differential equation in many applications. So I think that it is going to be very important for you. Let's have a look on what is the meaning and what is the form of the equation that we are going to deal with. This is the form, as you can see here. This is, as you can see, y double prime plus a function of x, which is the independent variable, times y prime plus q of x times y equals to f of x. So this is the form of our equation. This is the form of our equation. Actually, I want to highlight something here. This is the general form, but we are going to talk now about that each term of it is going to be important to understand, because some terms, if we go, for example, for the right-hand side here, this right-hand side, if it has a value, then we're going to call, or we're going to describe this equation to be a non-homogeneous. But if not, if it equals to 0, for example, we are going to call this equation to be homogeneous, as we're going to see later in the next slides. Why I'm saying this? Because it is going to give us the clue or the key for the solution, whether it is homogeneous or non-homogeneous. Okay, let's go here and see the understanding of it, and what is the meaning of the differential equation, and what is the meaning of the different parts of the differential equation. So to get some feeling for what we are dealing with, consider a simple example. We're going to talk about this example, for example. Y double prime minus 12x equal to 0. This means that y double prime equals to 12x, and we can integrate once to obtain. We are going to integrate our, let's have the laser pointer here. We're going to integrate our y double prime. We're going to integrate it once, so it is going to be y prime, as you can see, equals to the integration of the right-hand side, which is 12x dx, and this would equal to exactly 6x squared plus a constant of integration, right? Okay. If we're going to integrate once again, we're going to integrate the same equation once again, so we are going to obtain y of x equals to 2x cubed plus cx plus k. If we go back, this is our equation, so we are going to obtain, to integrate it again, then we're going to have this to be 12x, as we said, 2x cubed plus cx plus k. And this integral, when we are going to draw, we're going to draw the relation here between x here on the right, on the horizontal axis, and y in the vertical axis here. If we're going to draw this equation, remember that we have here c, which is an arbitrary constant, any number, and k, another number in the equation. This means that we have the integral curves for several choices of C and K can be seen in this figure. As you can see here, we have different curves, right? Why? Because this is actually based on C and K. We can put any value for C, any value for K, and then we can draw these curves, and there is no controlling points of it, right? This is the meaning of the integral curves. But what if that we are going to say that at specific point, let's assume that it's y equal to 3, where x equal to 0, we are going to look what are the curves that is going to pass through this point, which is the point, specific and particular point, which is x equal to 0 and y equal to 3. And this is actually what we are going to think about here. We are going to assume, let's assume that we have an initial condition where x equal to 0, our function is equal to 3. Based on this and substituting back in our equation, we're going to find that the k in our equation is going to equal to 3. So our equation becomes like this: y of x equal to 2x cubed plus cx plus 3, right? This is why, because we used what we call it an initial condition. An initial condition where x is assuming a value of 0 and the output function is going to be 3, which is the value of y, or the function. After substituting back in our equation, we are going to find that this is the equation. Let's draw this equation here on this graph. We have x here, we have y here, and this point, as I said, it is 0 and 3, which is based on the initial condition. This means that the integral curves are going to be, passing through this point. I forced all the curves to be passing through this point because I have assumed that I have an initial condition where y equal to 3 when x equal to 0. This is the point that we are talking about. So this is what we call it a selective or narrowing the number of curves needed, or the number of curves that is going to be represented by our integral. Then, if we look to these integral curves again, we can find that we have multiples of them and we have many of them. If we want a specific one, then we are going to do what? Yes, we are going to assume that we want one with a specific slope at this point. Let me use another color here. Let's use the green. So if we have this point here, and we have, for example, this one, okay, then for this curve, assume that this is the curve here, it has a specific slope here. So if we say that this is the curve that we are talking about, for example, at this point, there is, let me use another color here, we have, the slope here, okay, the slope here, let's assume theta, okay, the slope here is going to be unique for this solution. We call this curve as unique solution. Out of hundreds and millions of solutions, there is unique solution where this solution going to be obtained through this or through specifying the slope at the point that we are talking about. Let's assume this is the point that we are talking about, which is 0.0 and 3. So this means that in order to obtain a unique curve, okay, or a unique solution for our differential equation, we need to have first a point to pass through, for example, as we have obtained it from the initial condition, and we need to specify a slope. We need to specify a slope. This slope is going to be specified by also another initial condition. For example, we can assume that y prime of 0 equal to -1. This means that the slope y prime, it is the first derivative of the function, which means it is the slope of this curve at this particular point, at point x equal to 0, y prime should equal to -1. Then we have obtained this unique solution or this unique curve. Okay, so this is the meaning of having the integral. Let's go back again. Okay, so actually this is our main differential equation. Okay, this is the first derivative after having the first integration. Okay, and then this is going to be our solution after having the second integration. And when we draw this equation, we're going to find that we have multiple curves. If we want to go through or to select particular curve, we need two options. The first option is going to be specifying a point using the initial condition. For example, in our case, we specified that we want only the points, or we want only the curves which are going to pass through this point, which is, we specified it, okay, to be 0 and 3. And we need, among these curves, we are going to choose one solution. We call it the unique solution. Take care of this word because we're going to use it in the future many times. So we need to put another initial condition, which is going to be based on the slope. Okay, and the slope means that we are talking about y prime. This means in our initial condition, we have y should equal to value, okay, value, which is, in our case, it was sorry, let me erase this. Okay, so y here, y of 0 equal to a certain value, and we have the first derivative y prime of 0 equal to -1. These two conditions are needed in order to obtain the unique solution, Okay, let's go now and give some definition for the existence of a differential equation. Okay, the existence of the solution for the differential equation. If we look to our equation here, okay, assume that we have this equation, which is y double prime plus p of x, y prime plus q of x, y equal to f of x. If we assume that p, q, and f are continuous in an open interval I, means that they are continuous. This p, q, and f, they are continuous. Then the initial value problem, take care of this. I'm going to use this abbreviation from now on, initial value problem, P, IVP. This means initial value problem. What is the meaning of initial value problem? It comes from the initial conditions that we have. Value means that each independent value is going, or the independent variable is going to have a specific value. And this is the problem that we are talking now, which is initial value problem. Then we're going to say this equation, which is the differential equation, when we have the initial conditions to be based on y of x node equal to a certain number or a certain value, and y prime of x node equal to another number or another constant, then this equation is going to have unique solution on I. Okay, unique solution of I. That's the meaning of the initial value problem. This is the meaning of the initial value problem. Okay, so again, this is the theory that we are going to, from now on, to understand that whenever that we have a differential equation, second order differential equation, and we have some initial conditions which can be summarized as value of y and value of y prime at certain value of x, we call this to be an initial value problem. If we want to find the initial value problem, then there is a unique solution for it. Okay, having into or bearing in our minds that we have what? Some conditions that p, q, and f should be continuous. Okay, Now we have an idea of the kind of the problem that we're going to solve, and we need to put some strategy, okay, some strategy to start with the find how to solve our equation, Then, first of all, we're going to start with the homogeneous equation. So let's put it like title here, which is, this is going to be the I'm going to use this homogeneous equation, this abbreviation. The second order linear homogeneous equation has the form, this is the form. We're going to start with different forms or a specific form in the beginning, and then based on this form we are going to have our solution. As you can see here, what we have done here, or this form, is different than the original form. Let's go to the original form here that we started with. This is the original form, that the right hand side it has function, but here the right hand side is what? Exactly, it is 0. This is what we call it the form of the second order linear homogeneous equation. Okay, what is the solution of this homogeneous equation? Okay, the homogeneous equation, how we can find the solution for this. Okay, first of all, we are going to find something that is very nice for the homogeneous equation. Okay, we are going first to solve our differential equation to obtain what we call them linearly, linear or linearly independent solutions. Okay, this is what we are going to have in the beginning. So we're going to search for the two independent, okay, and they are linear solutions for our equations. Two functions are linearly independent on an open interval I, which can be the entire real line, and neither function is a constant multiple of other all x in the interval. What is the meaning of this? That if we're going to have two linearly independent solutions, we can put our general solution for the homogeneous equation as a C1 multiples of y1 plus C2 multiples of y2. This is going to be the general solution that contains every solution for the homogeneous equation. Okay, so let's put it in a solid form for you here. If we assume, let's assume that we have this equation, okay, y, let's have an example to understand what we are talking about. If we have y double prime plus y equal to 0, this is exactly, it is homogeneous, okay, homogeneous equation. Why? Because the right hand side now equal to 0. By inspection, you are going to find that we have one solution for this equation, which is solution number 1. It is going to be y1 equal to cosine x. If you substitute here y double prime, okay, of cosine x, it is going to be exactly, it is going to be the cosine, the derivation of the cosine, it will be minus sine, and then we are going to make another derivation which is going to be cosine, and y, it is cosine. So minus cosine, okay, this is minus cosine x plus cosine x equal to 0. So cosine x is going to be a solution for this homogeneous equation. And another solution, which is solution number 2, if we investigate it, we're going to find that y2 equal to sine x. The second solution for this equation is going to be sine x. That's right. The second derivative of sine x is going to be a minus form, and y is going to have the sine x, then minus sine x plus sine x equal to 0. Then it is another solution. We have two solutions now, y1 and y2. The first is cosine and the second is sine. Then we should look to y1 and y2 first. Remember, well, there is a condition that I put here. It is what? Yes, independent, linearly independent. What is the meaning of linearly independent? It means that we need, or we want to guarantee that y1 does not equal multiples of y2, the solution. I mean that this is the solution, okay? So if you look to cosine and sine, that's true actually. Sine x cannot be at all multiples of cosine x, right? Can you find that sine x, for example, equal k cosine x? Never. It will not happen, right? So this means that sine and cosine, they are independent solution, independent linear solution of the differential equation. Then the general solution, we call this the general solution, is going to be c1 cosine x plus c2 sine x, which is c1 y1 plus c2 y2. What is the meaning of the general word here? The word general here means that this equation contains all the solutions, all possible solutions of our differential equation. So why we didn't say that solution 1 is general solution? Because actually it does not contain all the solution of the differential equation. Here, c1x, if we put c1, for example, like 0, then we are going to have, and c2 equal to 1, then y3 is going to be sine x, which is one of the independent solution. And if we put c2 equal to 0 and c1 equal to 1, y3 is going to be cosine x, which is another independent linear solution. And if you are going to add them and sum them up, and every solution is multiplied by a certain constant, then it is going to be a solution for our differential equation. Okay? So we have now different techniques, or at least we have understood that for the homogeneous differential equation, we have, if we could find two independent linear solutions, then adding them up and multiplying them with constants, then going to give to us, this would give to us the general solution. This would give us general solution. Let's put, I want first to highlight here, let's go back again, yes. So that's the point here, that in this slide that I wanted to highlight, that for the solution, we're talking about the solution for the homogeneous differential equation. Our strategy for the solution is finding y1, which is considered to be, let's use the laser point, finding y1, which is what? Linear independent solution. How we can get y1? We are going to talk about this in the next lectures, okay? But now I want you to understand the main principle, the main idea, okay? So we are going to find y1 using some certain techniques that we're going to learn in the next lectures, which we are going to obtain based on which the y1, which is linear independent solution, and we are going to find another linear independent solution, we call it y2. Every one of them is considered to be independent solution, but they are not general solution. Every single one is not a general solution. Then, based on the theory that we are suggesting in this lecture, we are telling that if we could guarantee that y1 and y2 are independent, what is the meaning of independent? Means that y1 does not equal to multiples of y2, or y2 does not equal to multiples of y1, then the general solution of our homogeneous differential equation is going to be a constant times the first independent solution plus another constant c2 times the second independent solution. Okay, so this is simply the strategy of the solution for the homogeneous equation. Okay, the question here that need to be answered is how we can guarantee that y1 and y2 they are independent. sometimes it's a little bit difficult for us to see. Now in the previous example, we said that cosine x and sine x, they are independent. This is true because it is simply, we can say that sine x does not equal to multiples of cosine y. This is logic and straightforward and simple for us to verify. But what if that we have y1 and y2, a complicated equation that we cannot, by the first sight at least, judge whether they are going to be dependent or not. How we can guarantee this? This is what we are going to use. There is a kind of a check that needs to be checked first in order to say whether that y1 and y2 are dependent or independent. What is this check? It is the Wronskian test for independency. We call this the Wronskian, okay? The Wronskian test for independency. So what is the meaning of Wronskian and how it works and how we can check? You are going to find that if we have y1 and y2, which are the independent linear solution, or at least not independent now or not dependent, we do not know. We have two different solutions of our homogeneous equation. We have obtained them, as I said, using some certain techniques we're going to learn next lecture. Okay, then we can guarantee this or guarantee the independency by having the determinant or investigating the determinant of this Wronskian test. What is the determinant here? We're going to obtain the determinant which is y1, we're going to put it here, and y1 prime here in the first column, and in the second column we're going to put y2, the second solution of the homogeneous equation, and in the second row we're going to put y2 prime. Okay, then simply the determinant here is going to be y1 times y2 prime, y1 times y2 prime, minus y2 times y1 prime, y2 times y1 prime. Check this value. Okay, we are going to check this value. If the two solutions, okay, if the value of this Wronskian or the determinant is non-zero, then the y1 and y2 are going to be independent. Okay, so if this value of the determinant is non-zero, then y1 and y2 are considered to be independent. So we can put here two conditions here that is very important for us to fulfill and to understand for judging that our two solutions are independent. So let's suppose that we have y1 and y2 are solutions of our ordinary differential equations, the homogeneous differential equation, on an open interval I. Then the first thing or the first condition, okay, for this Wronskian, that this Wronskian is going to have only one unique value all over the interval. So we have the interval I here. Then the Wronskian should always, for all values of this interval, should always have one, okay, one value. And this is actually the first condition. Either the Wronskian of x equal to 0 for all x in the interval, or the Wronskian is going to be is equal or not equal to 0 for all x and y. What is the meaning of this condition? It means that the Wronskian should be always unique value in the interval I. So we cannot see, for example, or we cannot find that the Wronskian is going to be like 0 for some values for the interval and going to be non-zero for another part of the interval. No, this would not happen. This won't happen. Okay? So we have unique value for the Wronskian. And the second condition is, which is the important one for us, y1 and y2 are linearly independent on the interval I if and only if the Wronskian is what? Does not equal to 0 on this interval. Okay? Okay, so this is what I put it here in the red color. The solutions are linearly independent on I exactly when their Wronskian is non-zero on I. Okay, I hope that you can understand the Wronskian test, and now we are able to make an example for checking this Wronskian. Okay, let's go and have this example. Okay, check by substitution that y1, which is, we consider that we have obtained this linear solution, or the first solution, y1 of x equal to e to 2x, and y2 equals to x e to 2x. They are solutions for this differential equation, which is a homogeneous one. Y double prime minus 4y prime plus 4y equal to 0. Okay. So for all x, we need to check the Wronskian, right? So let's put, this is the first solution, which is e to 2x. We put it here in the first line, or the first row in the first column, and the derivative of it is going to be y1 prime. So the derivative of e to x is going to be 2e to x. And in the second column, we're going to put the second solution, which is x e to 2x. We're going to put it here, as you can see. And then in this row, in this cell, we're going to put the derivative of x e to x by the chain rule. As you know, it is going to give us e to 2x, and here suppose it to be 1, which is the x, plus 2 e to 2x times x, which is the derivation of the exponential function. If you going to multiply the diagonals and subtract them, so you have e to x, okay, times e to x, which is going to give us e to 4x, plus 2x times e to 4x, which is the second term here, times e to x, minus the multiplication of the other diagonal here, which is this value, 2x e to 4x. This equal what? Exactly, e to 4x. Can you think about this? It's an exponential function. It won't be 0 at all. And this is non-zero value. So y1 and y2 are linearly independent solution. Okay? So they are linearly independent solution. They are linearly independent solution. Okay? I hope that from this example you understand now what is the meaning of the Wronskian. It is straightforward and easy, and you are going just to check this like the 2 by 2 matrix determinant, and you are going to check the output if it is going to assume the 0 value or the value of 0 or not. That's it. Okay, now let's go to put a strategy for the solution of the homogeneous linear equation. We are going to put some strategy now for the solution of the homogeneous equation. Let y1 and y2 be linearly independent solution of this equation, which is the linear second order homogeneous equation. Y double prime plus py prime plus qy equal to 0. On an open interval I, this is the discourse, the interval that we're talking about. Then every solution on this interval I is a linear combination of y1 and y2. This is, we call it the general solution. Okay, so let's go through the explanation of this two sentences. This provides a strategy for finding all solutions of homogeneous linear equation on an interval, open interval I. Number one, the strategy is find two linearly independent solutions, y1 and y2. This is number one, and we are going to learn it next lecture. And number two, we are going to exactly check the linear combination, okay? I mean that we are going to find these solutions first, then we are going to check whether they are independent or not. If they are independent, then we are okay now. We can go to the second part of the strategy, which is that we are going to put them together in a way. We're going to say that the linear combination y equal to a constant c1 times the first solution y1 plus another constant c2 times the second solution y2. This contains what? all possible solution. All possible solution. We call this the general solution. We call this the general solution. For this reason, we call two linearly independent solutions, y1 and y2, we call this y1 and y2, we call them the fundamental set of solution. The fundamental set of solution on the interval. And we call this equation the general solution. Okay? So we have the fundamental set of solution and we have the general solution, which is the combination of the fundamental set of solutions. Okay? Then what will happen after that? Do you remember in the beginning I said that if we have constants in our equation like C1 and C2, this brings us to what? Let me use the pen here and recall what we have said. This is going to be something, if you remember the curves that we were talking about before, it's going to be, we have something like this. We're going to find many curves are going to be established. Why? Because we have C1 and C2. But if we could use initial condition, which is going to give to us some value of x, okay, at y, or the value of, or the value of the function at x equal to a certain value, and the slope, which is y prime, or the derivative of the function, also known, if we could obtain this from initial conditions given to us in the example, then we are going to use what we call it the initial value problem, and we are going to select one curve that is going to be unique, that is going to have unique, or going to provide for us a unique solution. Okay, so we have now like three different levels. Let me put it like this. Okay, so we have here y1, which is the fundamental set of solution. We call it set of solution. If you want to call it fundamental, it is okay. Fundamental set of solution. Y equal to C1 y1 plus C2 y2, we call this exactly the general solution. General solution. And then if we have values, or we have C1, okay, if we have C1 and C2, they are known for us using the initial value problem, we are going to obtain another type of the solution. We call it the particular solution. A particular solution, which is going to have C1 and C2 to be, or a unique solution, which is going to define C1 and C2 for us. Okay? Let's have an example so that we can understand it clearly here. Let's assume that we have, let's use the laser here, e to x and e to 2x are solutions of this equation, which is y double prime minus 3y prime plus 2y equal to 0. Therefore, every solution has the form, okay, we have obtained, this is what? The fundamental set of solutions. Then every solution, or the general solution, is going to be, we call this, let's use the, okay, we call this the general solution. This is what we call it, the general solution, which is going to be C1 ex plus C2 e to 2x. And this is the general solution of our equation, okay, of our main equation. If we want to satisfy the initial conditions, now these are the initial conditions, okay, which is, we assume that we have a condition where when x equal to 0, y is equal to minus 2, and also when x equal to 0, the derivative or the slope of the equation is going to equal 3. Choose the constant C1 and C2 so that we're going to substitute, back substitution in our equation, right? We have here y equal to C1 e to x plus C2 e to 2x, right? If we put x to be 0, then we have e to x here, which is going to be 1, e to 2x is going to be another 1, then we are going to have C1 plus C2 equals to minus 2. This is the first initial condition. And for the second initial condition, we need to have the derivative of this equation. We need to have the derivative of this equation. exactly, the derivative of this equation is going to be c1 e to x, because it's the same, plus c2 here, 2 times e to 2x. Let me put it here. It is simple and straightforward for you. So y prime here, y prime is going to be like c1 e to x plus 2c2 e to 2x, right? This is the first derivative of y. Then we're going to substitute with this initial condition in this 1, and we are going to obtain that y prime of 0 equals 3. So this means c1 plus 2c2 here equal to 3. From here we can obtain the values for c1 and c2. c1 minus 7, c2 equal to 5. And based on this, we are going to put our equation now. This is what we call it. Exactly, we call it the general solution. General solution. And now after putting c1 with minus 7, c2 with 5, we call this exactly the unique solution. We call this the unique solution. Okay? So this is the general solution here. Let's use the laser. So we have the general solution here for this. Based on the fundamental set of solutions, we obtain the general solution, which is combination of the two fundamental solutions. And then we have initial values, initial conditions, which is giving to us the value of the function at certain or particular value of x, which is x equal to 0, and the slope of the function at a particular value of x, which is when x equal to 0, then y prime is going to equal 3. Then based on this, we substituted in the equation and the derivative of the equation, and we obtained c1 equal to minus 7, c2 minus equals to 5, and then we substituted in our equation here, we obtained the unique solution. What is the meaning of unique? It is one single curve we have selected one single curve out of the multiple curves that we have drawn. This general solution would give to us multiple curves. If you remember, if I go back here, yes, this one, or let's go here. This is the general solutions. These are different curves. Every curve is considered to be a unique solution. So the equation, whenever that it has c, which is a constant, and k, which is another constant, this means that we have multiples of solutions for different values of c and k. But if we are going to use the first initial condition, okay, the first initial condition, which is, let's assume that y equal to certain value when x equal to 0, then we have put all the curves the curves which are going to pass through a certain number here or a certain value for y, we put them together. Then we put a narrow range for the general solution. After that, we are going to use unique solution, as I said here, unique solution, by assuming that we know the slope here, which is exactly y prime equal to a certain value when x equal to 0. Okay, so actually this is what happened in our equation here. Yes, this is what happened here. This is the general solution. This is going to give to us different values or different curves. This one is a unique solution. How we can obtain it? We are going to integrate 2 times, so we need 2 different initial conditions, one of the function, another one of the slope of the function at certain point. Here we chose it to be when x equal to 0. When x equal to 0. Okay. Now we have obtained remember that here we are talking about what? A differential equation where the right hand side is 0. This is the form that we started with, okay, which is the homogeneous equation. What if that the right hand side is non-zero? It is a function. So let's go back again to start what we, yes, this is where that I said that this is the homogeneous one, and this is where that the right hand side is going to be 0. But actually there is another case where that we have the right hand side is not going to be 0. The right hand side is not going to be 0. So we have the same left hand side, y double prime plus p of x y prime plus q of x y equals to exactly a function called f of x. We call it f of x. So there is a difference between the homogeneous and non-homogeneous. In the homogeneous equation, the form of the equation itself is different actually. We have the right hand side is going to be 0 here. The right hand side is going to be 0. But in the non-homogeneous, the right hand side is going to be a function of f of x. This is from the form point of view. But actually from the solution point of view, there is a great deal of difference between the non-homogeneous equation and the homogeneous equation. What is this difference? I put it here in red color. The main difference is that the sums and constant multiples of solutions need not to be solutions for the case of the non-homogeneous. Do you remember? We said here, let's assume that here for x1, if you remember, we said that we have y1 and we have y2, which are the fundamental set of equations. Then we said that our general solution is going to be c1y1 plus c2y2, right? This is for the homogeneous. For the non-homogeneous, this won't work for us. It will not happen. The constant multiples of the solutions need not to be solutions. So we need to have a different strategy. We need to have a different strategy. Okay? So how we can find the general solution for the non-homogeneous? So there is some derivation, but I skipped it actually here, but we want to go through the understanding directly of the strategy. So first of all, we need to find something called yp, which is the particular solution. We call this yp, let's assume it to be any solution for the homogeneous equation. Sorry, this is supposedly to be non-homogeneous here. I think this is the mistake. Okay, so this is actually the non-homogeneous equation. This is non-homogeneous. Okay, homogeneous, non-homogeneous, and this is the homogeneous one. Okay, so that you do not like confused with this. So we are going to find the way to obtain yp, capital YP, which is a particular solution of this equation. Okay, we're going to call it yp. First, let me use the pointer. Call it yp here, which is the solution for this equation, the solution for this equation. How we can obtain this yp? Next lectures, we are going to know how to obtain this yp. And then we are going to assume that we have, for the same left-hand side, we're going to equate it to 0 here. So we're going to say that there is a homogeneous equation in this case, which is equal to 0. We call this the associated homogeneous equation. So we are going to assume that we know y1 and y2 for the homogeneous equation, which is y1 and y2 are considered to be linearly independent solution of this equation. Then the general solution of the non-homogeneous equation is going to be written as this: c1 y1 plus c2 y2 plus yp. This is what we call it the general solution, as I put it here, the general solution of the non-homogeneous equation, which is this equation. Okay, so this is what we are going to use to solve this what we call it the strategy. This is the strategy for solving the non-homogeneous linear equation. Okay, then let's put it in a kind of steps for finding the solution of the non-homogeneous equation. We can find, like, we can put it like in 3 different steps here. So number 1, find 2 linearly independent solution, y1 and y2, of the associated homogeneous equation, which is, what is the associated homogeneous equation? It is the same left-hand side of the non-homogeneous equation, but we are going to equate it with 0. That's it. This is going to be simple and straightforward. We can obtain y1 and y2 easily. Then we're going to check that y1 and y2 are independent solutions. Then they are considered to be the real solutions for this homogeneous equation. Step number 2, we are going to find any particular solution, y, capital Y, p, okay, p, y particular of what? Of the non-homogeneous equation, which is y double prime pxy prime plus qxy equal to fx. From where we can get this particular solution? We are going to learn some techniques next lectures, okay? Then, number 3, the general solution of the non-homogeneous equation is like this: c1 y1 of x plus c2 y2 of x plus y particular, in which c1 and c2 can be any real numbers. They are constants. And if we want to know c1 and c2, we need to have at least 2 initial conditions. 2 initial conditions. Okay, this can be done in our initial value problem. Okay, so this is actually, we can say this is the strategy for solving the non-homogeneous equation. Okay, simple and straightforward. Let's have an example and wrap up after that. For the non-homogeneous, let's assume that we want to find the general solution of this equation, which is y double prime plus 4y equals to 8x. This is non-homogeneous because the right-hand side is non-zero. If you looked at this, let's assume that we know so we are going to talk about the left-hand side and equate it to 0 first. So we're going to say that we have y double prime plus 4y equal to 0. This is the associated homogeneous equation. And we can find the linear or fundamental set of solution for this equation, which is going to be exactly sine 2x and cosine 2x. They are going to be solution for this. If you put y double prime plus 4y equal to 0, if you have this is y1 and this is y2, you can find that these y1 and y2, they fulfill this equation. You can try it by yourself if you need. Then we are going to assume that we have y particular. So we started with y1 equal to sine 2x, y2 equal to cosine 2x. These y1 and y2, they are the solution of the associated homogeneous equation. Then we're going to find another particular solution of this non-homogeneous equation. We call it 2x, yp equal to 2x. Then the general solution for our equation is going to be c1 sine 2x, this is y1, plus c2 cosine 2x, which is y2, plus the particular solution 2x, which is y particular 2x. Okay, so this is the general solution. This is the general solution for our homogeneous, non-homogeneous equation. Okay, if we want to know what is the value of c1 and c2, we need to provide some initial condition. Let's assume that we have initial condition at x equal to pi. So y of pi equal to 1 and y prime of pi equal to minus 6. These are the 2 initial conditions that we've got in our hands right now. So, and this is our initial, or this is the non-homogeneous equation. Then we're going to substitute actually. So here, in our equation, we have y of pi, which is this, the general solution. We have c1 sine 2x. Sine 2x, which is sine 2 pi, means it's 0. So it is already cancelled here. And then we go to the second term, which is c2 cosine 2 pi plus 2 pi plus 2 pi, 2x. This would equal to c2 plus 2 pi equal to 1. And from here we can obtain c2 equal to 1 minus 2 pi, right? And for the first derivative of this equation, which is y prime of pi, it would equal to exactly 2c1 cosine 2 pi minus 2c2 sine 2 pi plus 2, which is, instead of 2x, the derivative is going to be 2. Then we have 2c1 plus 2 equal to minus 6. This is from the initial condition. This means that c1 can be obtained easily as minus 4. Based on this, our unique solution here, this is the unique solution. Let me highlight it here. So this is what we call it, the unique solution here. Okay, unique solution is going to be of the initial value problem that we are talking about, y of x equal to minus 4, exactly, 2x, and here this is exactly, this is c2, right? This is the c2, cosine 2x plus 2x. This is what we call it the unique solution. This is the unique solution. I hope that we can understand, or we have understood what is the meaning of the strategy for finding the solution for whether for the homogeneous or non-homogeneous. To conclude this, I'm going to say that we have explained in this lecture two different strategies for the solution of homogeneous and non-homogeneous. First of all, we started with the general form of our linear second order differential equation, and we said that in the right hand side we have two alternatives. Maybe f of x equal to 0. In this case, our equation would be called homogeneous differential equation, or f of x is going to be really a function of x. In this case, it will be non-homogeneous equation. We started with the non-homogeneous equation, and we said that we are going to find the solutions for the non-homogeneous equation, where that the right hand side is going to be 0. And we said that the solution is commonly to be like this. We are going to obtain some solutions, which is y1 and y2. We call them two linear independent solutions. And then the combination of them is going to contain all the possible solutions, which is going to be a multiple constant or constant multiples of y1 plus another constant multiples of y2. This, we call it the general solution. So we need to guarantee that y1 and y2 are independent. Then we checked something called the Wronskian test. We put y1 and its derivative in the first column, and y2 and its derivative in the second column, and get the determinant. We found that we need, if y1 and y2 are going to be linearly independent, we found that our Wronskian should not equal to 0. This is the main condition for us. And we put another important condition here, that Wronskian is going to be unique over any interval that we are studying. So, based on this, we have solved or found the way for the homogeneous linear equation solution. We said that first we need to find two linearly independent solutions, y1 and y2, and simply the linear combination of c1y1 plus c2y2, it is considered to be the general solution. That's it. Then we jumped into some examples and went to the non-homogeneous linear equation, how we can solve it, where that the right hand side is going to be f of x. We simply said that there are three different steps that is going to be followed. The first one is finding y1 and y2 of the associated homogeneous differential equation, which already we have explained before, and then find any particular solution, yp, capital Yp, of the non-homogeneous equation, this equation, how we can obtain it from the next lecture, or next lecture maybe we can obtain, or we can find the way for Yp, and then the general solution of our non-homogeneous is going to be in this form. C1y1 plus C2y2 plus yp. This is the general solution, in which C1 and C2 are going to be any real numbers. And if you want to obtain unique solution for this non-homogeneous equation, we need to provide two different initial conditions, one to obtain C1 and another one to obtain C2. Okay, that's it. And let's have our homework for this class. We have like 5 different problems here. They are all of them linear second order differential equation. And if you look to all of them, you're going to find that the right hand side equal to 0. We're talking about exactly homogeneous differential equations. And we provided here the initial conditions, two initial conditions for y and y prime. Okay, y and y prime, and we provided the solution for them as well. So the point here, what you should do is verify that y1 and y2 are solutions of the homogeneous differential equation. How we can verify this? Yes, verify means that you're going to substitute with y1 in this equation and y2 in this equation and see whether that y1 and y2 really considered to be solutions for the equation or not. And then calculate the Wronskian of these solutions as we have learned. And then write the general solution and then solve the initial value problem, because we have here an initial value problem, because we have y equal to -5 for x equal to 0 and y prime equal of 0 equal to 2 when x equal to 0. So we have initial value problem. You can upload your assignment on the iCampus, on the canvas, or I mean that on the system, so that you can actually remember that the assignments and your attendance as well is going to be considered together. So whenever that you send your assignment, this means that you have attended the class and you have watched the video. Okay, so take care of this. You can put it in the assignment section of the iCampus, your solution. Okay, thank you. This is actually concludes what we have to say, all what we need to say about our class for today. It's an introduction, considered to be an introduction for the linear second order differential equation, and highlighting the strategies of homogeneous equation solutions and the strategies for the solution of the non-homogeneous. I hope that you like this, and I hope that you can make your assignment easily. Thank you, and see you next time.